All right. Should be recording. Ready. Fire this calculator up. Gen Chem 1, practice exam 3. Normally, I would start this exam by listing out all my gas laws and which one went to which person. But I'm looking at my reference sheet over here, and we give you all the gas laws, and we tell you which one's which. Well, that's just too easy. We give you root mean squared for the speed of the gas. We give you Graham's law, which is used for effusion. We give you all the temperature and pressure conversions. We've got the equation for heat. We've got a periodic table with more sig figs, and I'll probably use. All right, so well, hey, I'm gonna jump right in there. All right, so sample of nitrogen gas N2 at a volume of 22. Well, that's the next convention somebody needs is a dry erase mouse. Apologize, I'm drinking root beer, maybe a little gassy. I thought it was appropriate for the gas test. All right, so no, just make a list. What's given in this question? Number one here, given. I got 22.4 liters. I got 3.00 moles. And then I've got 40.2 liters. And what do they want? They want moles. All right, so I've got a volume, a number of moles, a volume, another number of moles. 22.4 contain 3 moles. So those two go together. I'm going to give them ones. I'm going to give these twos. Now, I would start this. This is Avogadro's gas law. I'm going to go ahead and do it the long way. V over T. So I'm going to do V1 over N1 equals V2 over N2. Now, you could certainly flip those. That's the way it's usually listed in the books. I need to make sure everything's in the appropriate units. So liters and moles. Looks good. So V1 is 22.4. N1 is 3. V2 is 40.2. N2, we don't know. So we're going to do some cross multiplying and then some division. So I'm going to have 3 times 40.2 divided by 22.4. That'll give me my N2. And I get my fancy calculator. 3 times 40.2 4. Easy enough. I got 5 point, let's see, sig figs. I think had 3. Let me keep this at 5.38. My units will be moles. And that's number 1 done. All right. I got a better pen. Okay, no problem. Maybe even have room to write bigger. We'll see. Okay, so howdy, man, this is not too bad. Let's go ahead and do the next one. So I'm just running through this practice test. Give us some practice on these. Let me see. So you'll notice that I didn't worry too much about the multiple choice options. I don't even know if I changed any of those, so don't pay any attention to the multiple choice. I was just taking it from the previous exam. 710 millimeters mercury, 1.90 liters, 350 Kelvin, 0.700 liters, 300 Kelvin. I got all kinds of stuff going on here. And it says what they want is a pressure. All right, so this is a pressure, this is a volume, a temperature. I've got another volume, another temperature, another pressure. So let's double check. Uh, Gas sample, pressure of 710 millimeters mercury with a volume of 1.9 liters and temperature of 350 Kelvin. So those all went together. So decreases to a volume of 0.7 liters. That's my new volume with a new temperature of 300 Kelvin. What is the new pressure? All right, so this is the combined gas law, but it's PV equals nRT, pressure, volume, and temperature. P1 V1 over T1 equals P2 V2 over T2. I want P2, so I'm going to go ahead and multiply both sides. It's T2 over V2, T2 over V2. And so that these will cancel out. And then I want to double check, make sure I have everything in the right units. All right, so Kelvin and liters, I need the appropriate units for pressure, 710 millimeters mercury, 760 millimeters mercury is 1 atmosphere. So let's go ahead and 760. I got 0.934 ATM. All right, so I think I have room here to go ahead and write this all out. So, or maybe we'll just do it right here. T2 is 300. P1 is 0.934. V1 is 1.9. And when I type this in, I'm going to need new parentheses on the bottom. V2 is 0.7 times T1 is 350. All right, most common places people miss it. They don't put things in the right units, especially Kelvin is particularly bad about that. Or they forget these parentheses on the bottom on a tougher problem like this. All right, so wish I could just type this in on a regular keyboard, but we got it. All right, so I'm making sure I open parentheses here. I'm not going to close them because it'll close it automatically. So 2.17, next digit would be 3, and this should be in pressure of ATMs. Let me double check here. Temperatures, the kelvins will cancel out, the liters will cancel out. I'm left with ATM. So double check your math, plug the units in. I like to do that actually before I do the number. So notice I did it after. It's kind of the physics way of doing it. I like to plug it in first, double check my algebra. But hey, here's my answer. Does that make sense? It's more pressure, but the volume is about half, a little bit, so a little bit less. And even though we cooled down, we saw much more of an effect from changing the volume. So yeah, well, by that, the pressure had to go up. Boyle's law says pressure and volume are inverse. So the next one, I see a gas is compressed under constant temperature conditions. The original gas was 1 atmosphere, so let's make another list. This is number 3. So 1 atmosphere. We went from 6 liters to 2 liters, and they want to know the new pressure. So this is a pressure 1, volume 2, pressure 2. Always double check which things go together. All right, so this again, Boyle's law, P1 V1 equals P2 V2. things in the appropriate units. So I can just plug this in. 6 is equal to P2 times 2. And so 6 divided by 2 will be, is that going to be right? Yeah. 3 is my new pressure. 3 atmospheres. So my volume decreased by a factor of 3. So I've got a third of the volume, which means my pressure had to go up 3 times. All right. That makes sense because these are inversely related. All right. Let's see. I can't. Problem here is I can't see which ones you guys can see. So that was 3. Let me scoot all the way up here to 4. You should be able to read it now. All right. So 4. What is the temperature of a gas sample that's found in a hot oven? Its original volume was 40 liters at a temperature of 25 degrees Celsius when placed in the oven. The new volume is observed now to be 63.9 liters. All right, so we got all kinds of stuff going on here. So I got 40 liters. I got 25 degrees Celsius, 63.9 liters. What is the temperature? What they want is a temperature. All right, so I've got a temperature, a volume. 25 and 40 go together. So those two be my ones, and these are my twos. Temperature and volume, that's Charles's law. PV equals nRT. So volume 1 over temperature 1 equals volume 2 over temperature 2. After volume and temperature. And oh, they tried to get sneaky. I got the temperature. Charles's law is only true if this is in Kelvin. So this is 298.15 Kelvin. So now when I go plug this in, it's not so bad. I've got 40 over 298 equals, we're going to make an X down here, and 63.9. So 63.9 times 298 divided by 40. Not showing all my algebra steps. That's why I don't teach algebra. On 63.9 times 298 divided by 40. 476. But that's Kelvin, so that's not too bad. Let's get a rough idea of what happened here. We didn't quite double, but we increased the temperature. The volume should have gone up. Maybe about 50%. Yep, I'll buy that being about 50%. Okay. Yeah. A bit more than 50%. Yeah, I'll buy that. Remember, volume and temperature are direct because it's division. So you'll notice every time I work these, I stop and I say, hey, does my answer make sense? All right, the next one, oh, I got all kinds of pictures, and it says a gas was collected in a eudiometer, and they got a pretty picture. The mixed gas was equalized to atmospheric pressure. All right, so that's just a nice little trick we use. And then the mixed gas volume. So here's my volume. So here's my given. So the volume is 43.95 milliliters. And the pressure, they said, was 734.81. And this is the total pressure. They're not telling me that, and I'll show you in a minute why I know that. And the temperature is 20 degrees Celsius. And then they say, what is the pressure of the H2? And the vapor pressure of water is in the table. So they mention pressure H2O. We're going to go to the table. All right. So we're collecting something over water. So I got a tube. Bloop, bloop, bloop. It's in water. Bloop, bloop. All right. And so inside here, anytime you collect anything over here, so we're collecting H2 and water vapor. And water vapor only depends on the temperature. So we're going to be applying a little Dalton's law here. And then let's see what else we want to do. They just want the partial pressure. This is what they want of the H2. All right, so I have the total pressure. I have the temperature. I don't need that volume right now. Okay. Now, if I had that volume, then I could see I have volume, pressure, and temperature. I could find the number of moles that would be in, but I'd have to have this pressure of the H2, but I could find that. So first question, it says, find this. And we might come back and get that later, a number of moles. And why am I looking at that? It's because this is one of my gas laws. And you guys can't read that. Too high. Got it down over here. This is my ideal gas law that I keep writing. And so R is a constant. So if I knew all the others, then I could find the number of moles. But let's go ahead and work this one. This is actually really easy. Pressure of the total is the pressure of H2 plus the pressure of the H2O. Now we are at 20 degrees Celsius. So at 20 degrees Celsius, this is 17.535 millimeters mercury. Oh, man. And the pressure here was in millimeters of mercury. So I'm going to go ahead and take this into atmospheres. You have your choice here. You could do all your work in millimeters of mercury, but it's just so much easier if I have to do this problem later. So first thing I would do actually is I'm gonna come down and I'm gonna look and see if this one I didn't give us any options on A, B, C, and D. If I had that, then I would go ahead and do millimeters mercury, but I'm gonna go ahead and take this to ATM. Let's get a nice easy answer here. So 734.81 divided by 760. And then I'm going to go ahead and do this all at once here. 17.535 divided by 760. You'll notice I went ahead and did the subtraction. And so subtracted that out. And so this, all I did here was subtract these. And that gave me 0.94, we'll call it 4 ATM. And let's get a little reality check here. 734.81 divided by 760. It's 0.96. All right, I'll buy that. Okay, so then it says what mass of hydrogen was collected. Oh, okay. So which mass of hydrogen was collected? Let me scroll down where you guys can see that. What mass is hydrogen collected here? So here now I can use my ideal gas law. If I have the pressure, this is pressure of my H2. I have the temperature, that will be 293.15 Kelvin. The volume here, I'm gonna go ahead and turn that to 0.0 I can't remember if you guys can see that. 0.43. Nope. I apologize. 0.04395 liters. And okay. So let's just show this some algebra here. PV equals nRT PV divided by RT will be N. The pressure is 0.944. The volume we had was 0.04395. Well, that's probably a pain to read. 0.08. I'm going to just round that. And then temperature here was 2. I'm going to round that to 293 as well. So I got multiplication. I need parentheses on the bottom. Don't forget that. So here's how I'm going to type it in. 0.944 times 0.04395, and then divided by open parentheses 0.0821 times 293. So this multiple choice, I use 0.0821. If you're on the test, you might want to just go ahead and use the R we give you, which probably, let me double check how many sig figs we give you. We give you 5 sig figs. Okay, 0.082058. That's fine. Be careful. There's 2 different R's. So ideal gas law, we use 0.082 value. And then if it is the root mean square, that's when we use the other R. Luckily, they're together on the test so that you can differentiate which one. All right, so double checking here. This is going to give me moles. I got 0.001725 moles of H2, but it said how many grams? So each 1 mole is 2.016 grams. Remember, because it's 2 times 1.008, so I got that number. This came off the periodic table, which you guys can't really see, but so I'm just going to take this and multiply it by 2.016. And now I get over here the big whopping answer 0.00348 grams of H2. And which gas law did I use after that? I used the ideal gas law. Okay. Then we get a whole bunch of these. Which one did we use in question 1? I answered that at the time. I'll let you guys go back and see those. The easiest ways you're looking for these variables. So I'll skip those for now. Let's start. So normally I would look at those, and those could be quite difficult, but with what we're given on this test, not too bad. So it wants us to find, so we're going to take magnesium, react it with HCl. We get 2 HCl to get magnesium chloride plus hydrogen gas. And it wants to know if I have 18.61 grams of magnesium, and I want to take this to it says to STP, and I want volume of H2. All right, so let's come back here then. So things that were given, 18.61 grams of magnesium. This goes to my number of moles of H2. STP, temperature is 273.15 Kelvin or 0 Celsius. But I'm going to go ahead and do that conversion, in 1 atmosphere. So I've got temperature, pressure, number of moles. They ask for volume. This is ideal gas law. Okay. So volume is nRT, variable R over P. So volume will be, I need to go ahead and do that math here. So I'll come down here and do this. 18.61 grams of magnesium. I'm going to use the molar mass of magnesium. Go to moles of magnesium. And for each 1 mole of magnesium, I get 1 mole of H2. And looking at my periodic table, oh, that's tiny. 24 point. Ooh. See if it's even bigger on our screen here. And 24.31 on the one I can actually read from across the room here. 24.31. This will get me to moles. So let's go ahead and type that in. 18.61 divided by 24.31. That'll give me the moles of magnesium, which then is the same because this is balanced. Good. So this will be 0.766 moles of H2. Now I can plug this in. 0.766 R 0.0821, just to get a rough idea. 273.15. Pressure is 1. Now, we could have memorized this idea of 22.4 liters and applied that here, but it's just easier to plug it in. So let's go ahead and do our answer times 0.0821 times 273.15, and volume 17.17 liters. Now I'm going to come back and double check something. I'm going to take this number and multiply that by 22.4. And I get the same answer, roughly 17.1, 17.2. So, okay. I'll buy it. I'll buy it. That'll get me close enough for multiple choice. So that'll be number 12. And then it says, 13. Changing gears quite a bit. 13 here says, arrange the following ideal gases slowest to fastest through an evacuated tube. All right. So evacuated tube. All right. Slowest to fastest. So I'm going to be thinking about my root mean square equation here, which has 3RT, square root of 3RT over M, where M is in kilograms. So what that's going to mean to me is slow is big and fast is small. So slowest to fastest, I'm going to just do the numbers first. 64, 44, 40, 30, 28, 22. And then I'm going to play my matching game. This is H2, 20, and you see how it's done. I'm not even going to bother doing the rest. So the key was slowest mass. Biggest mass, the slowest. Okay. Similar kind of question here based off of that. And it says, do CO2 at 0.00 degrees Celsius. Oh man, we gotta type this in. Now we give you the equation. We've got to type this in. So let's look at this crazy equation. This URMS equals the square root of 3RT. Now be careful, it's a different R here, and it's a different M. This is one of those. Oh, I hate this M. This is M is in kilograms per mole. And R is the 8.3145. Okay. And that's in moles over joules over moles over Kelvin. So we're going to get an answer here. Temperature will be in Kelvin. We'll have, okay. So square root of 3 times 8.3145 times 0 Celsius is 273.15. All right. Now this is CO2. So see if I got room over here. CO2. So I got 12.01 plus 2 times 16. That's 44.01 grams per mole. That's the molar mass. And so this will be 0.04401 kilograms per mole. I moved it 3 places. Okay. So that goes down here, 0.04401. Now we can type all this in. Oh boy. So second square root. And I want 3 times 8, 3145 times 273.15, and then divided by 0.04401. There. I got 393. All right. So, hey, that's we got it. Yay. Couple of keys there. Make sure you put that in Kelvin. Make sure you put this in kilograms per mole. Crazy units. So the equation itself, the math isn't super hard. It's knowing what units to plug everything in. We've got a few. Dr. Milligan was nice enough to give you quite a few little pointers there. You'll notice it's temperatures in Kelvin, and he gives everything kind of right there beside it. So that helps. That helps. All right, I've got some kind of reaction here and a bunch of heats of formation. And he says, what is the enthalpy change? All right, so delta H equals H of the products minus H of the reactants. Okay, so let's do C2H2. Let's just go ahead and write the whole thing. 5O2 goes to 4CO2 plus 2H2O. And this really is as simple as I find the O2. It's a gas, all right, and it's 0. So I'm just going to get rid of that. C2H2 gas is 226.73. So I'm going to do 2 times 226.73. And then over here, I've got CO2, and I've got 4 times negative 393.509. And then I've got water plus 2 times water, which is, wait a minute, this is water that's a gas, so be careful about that. Negative 241.818. And so we can go ahead and add those up and then subtract out this one. I'm just going to bring this over here. I'm going to do minus 2 times 226.73 and start doing this math. So notice I could ignore the O2 because it doesn't really count for anything there. All right, clear. 4 times negative 393.8509 plus 2 times negative 241.818 minus 2 times positive 226.73. Yeah. And I got negative 2511. Hey, that's an answer here. Let's see, these are in kilojoules. So kilojoules, yep, I'll buy that. Now I got negative. So because it's negative, this tells me a whole bunch of things. So I'm going to make a list over here. I like to memorize EXO. It's got negative delta H. It's the one that has picture like this that goes kind of downhill. It has heat goes out, and heat is a product. So then it says, hey, which one is it? Oh man, you gotta have that memorized. So I said that's XO, but negative delta H. Now I actually used the negative delta H to know that it was exothermic. So double checking your math and double checking this. So it should be the one that's going downhill. In other words, the reactants will be over here, which I'm not sure if you guys can see it. The reactants are going to be on the left, the products are on the right, so there's less energy in the product side than there is in the reactant side. So products minus reactants. All right, we've got extra energy that got sent out, so this is exothermic. Okay, so this will be plot 1, and it should be exothermic. Oh, they hit us again. So 16 and 17 are just kind of, if you know it, it's free points. If you don't, ooh, you're in trouble. All right. So, ooh, I hate that. Hate that. So make sure you learn, either exo or endo. Okay. So, uh, 18 is this one that says CO2 effusion to N2. All right, CO2 to N2. And so let's just take this M2 over square root M1. Now, even if I'm dividing that by 1,000, it's going to go away. So they want related to. So I'm going to put CO2 on the. So I'm going to do CO2 to N2. So this is my 1 and this is my 2. All right. And so the CO2 will go on the bottom. This will be 28. 2 times 14.01. 20.02 will be fine. That's my N2, right? That's that one. And this is 44.01. And let's go ahead and just type these in. So second square root of 28.02. Use that right arrow to get out of there. Divided by second square root of 44.01. And it says it is 0.798 if I'm doing it that way. So CO2 is roughly 80% of the into 0.798. Okay. 21 here. I got a whole bunch of stuff going on. I got, ooh, I'm gonna write this down. I got so much going on. Better write it down. So I've got given 30 milliliters, a zero point 0.2 molar NaCl. So those two go together. I got 10 milliliters, a zero point 0.1 molar AgNO3. And they gave me a formula. I'll go ahead and write that down. What? No, that's a typo. That should be a CL there. Uh, yeah. Okay. And so let's see. It asked me about this. Total mass of this is measured. So let's go ahead and get the mass. It's 150 grams. And then temperature. Wait a minute. It says temperature is 22.1 degrees Celsius. And it went to 23.2 degrees Celsius. All right. Now that's a pretty good hint there. And then once it tells me the specific heat of H2O is 4.18 joules per gram times degrees Celsius. All right, so joules. And it wants delta H. Now, usually delta H is going to be in for the reaction. All right, so here's our kicker on this. We got a couple of different things going on. First thing that we're going to look at is the fact that we know how much mass of solution we had, mass of water and everything. There's my mass. That's an M. Here's my delta T. Then I got specific heat. So if I want to know that energy, I can use our equation here. Q equals mass times specific heat times delta T. And so this will be 150 and it's over grams. So times 4.18 times my delta T final minus initial. So that's going to be 23.2 minus 22.1, 1.1. So we can go ahead and just multiply these. 150 times 4.18 times 1.1. I got 689.7 joules or 0.6897 kilojoules, whichever one they're asking for. All right, and then it says, what is the limiting reactant? Okay, so limiting reactant on this, I can figure out how many moles I can make of each one. So notice I had to make that change. So I'm going to mix these two together. So I've got 30 milliliters. Can we see? Okay. I'm going to change that 1 milliliter is 10 to the minus 3 liters. And then I'm going to multiply it by 0.2 moles for 1 liter. So I'm using molarity, this 0.2 here. And then this one is 10 milliliters. Same idea. 10 to the minus 3 liters. 1 milliliter. And this is 0.1 mole per 1 liter. And since they're 1 to 1, whichever one I run out of first is my limiting reagent. So 30 times 0.2 times second EE 3 and 10 times 0.1 second EE negative 3. All right, so this is 0.006 moles, and here I only have 0.001 moles. So the limiting reagent is my AgNO3. We run out of it. The thermicity. All right, so thermicity, in other words, is it exothermic or endothermic? Now, the heat gained was a positive 689.7. But keep in mind that the heat gained is negative heat lost. All right. And so that means my reaction, so the water got warmer when I did the reaction. So the water gained heat, which means my reaction lost heat. Remember, losing heat, exothermic, and that is negative delta H. What kind of reaction is this? It makes it solid. So it's a double displacement that is a solid. So that's D. So it's precipitation. Double displacement, that's a precipitation. All right. 35. How many grams of water must be produced to make 15 million kilojoules of heat? Ooh, that's a lot. Molar mass of water is this. So we're going to do this reaction and make 15 million. Ooh, let's erase a lot of this. Yeah. I'm mumbling my way through. Haha. Studying by Boomhauer. So I'm going to type this in 15 E6. And I'm going to divide that by this 802.3. And I've got to do this reaction 18696 times. In other words, I need to do that reaction, and it says how many grams of water. So each time I do this reaction, it gives me kilojoules, right? And so I need to multiply this by 2 because I need 2 moles of water for each one reaction. I'm just going to write reaction. One reaction gives me 2 moles of water. And so here, I'll tell you what. We're going to write it up nice and proper. 15 times 10 to the 6th kilojoules for every 2 moles of water I make negative 802.3 kilojoules. We'll just use the number. Don't worry about the negative. And wait a minute. And it wants to know how many grams of water. All right. So each 1 mole of water, I need 18.016 grams. And that's it. So now I can come in and type in 15 second E6 divided by 802.3 times 2 times 18.016. And I got 673,663 grams of water. All right. So, gonna be heat reacting this, we're going to make a lot of water in order to make this number of kilojoules. Oof, that is a lot. So let's see. So it's a gigajoule. That would be a terajoule, 15 terajoules. Oh, man, that's a lot. All right. Oh, here's an easy one then. Okay. Given the reaction and its enthalpy value, what is the best description? That's the same reaction. So it's negative, so it's exothermic. There's 2 mole. There's that for 2 moles. Nope, it's 1 mole. So exothermic. There's this produced. Right. Notice this heat is going to be on the product side, right? And so because it's negative, and so heat's produced for every 2 moles of water. Hey, if you had that, then this problem's a lot easier, man. All right. 27, it says do Hess's law. Okay, so Hess's law here. CS2 plus 3O2 goes to CO2 plus 2SO2. And we're given C. I'm not going to worry about the states of matter. Goes to CO2 at negative 393.5. And you know what? Get the numbers out of my way. And then I'm going to do S plus O2 goes to SO2. And C plus 2S goes to CS2. All right. So the first thing I'm going to kind of do, let's change colors here. So this is what we're kind of given. I want to get each of these. So I need a CS2. I'm going to flip this one. So I need CS2 plus 2S. Oh, sorry. Goes to 2S. So this one I did the negative. And let's just do C plus 2S. So that gives me my CS2. Now I've got O2s over here. I need a CO2, so that one's fine. I got SO2, that one's fine. Wait a minute, I need 2 SO2s. I need 2 SO2s. All right, so that means I need to take this one and multiply it by 2. Now I can add these up. All right, so when I flip that one, I'm going to rewrite that again. CS2 goes to C plus 2S. Just gonna scratch that out. Okay. I've got carbon. I got 2S. I've got 2O2 and 1O2. That's 3O2. And I got CS2 goes to, here we got CO2. Now I've got 2SO2. And I'm going to go ahead and write it down here. Plus C plus 2S. All right, I've got carbon on both sides, 2S on both sides. 3O2 plus CS2 goes to CO2 plus 2SO2. All right. So this is the math we had to do. So I'm going to come back in. Whatever I did to the equations, I do to my math. So this was 393.5 plus 2 times negative, oh, that's negative, sorry, 296.8. And then I flip this one, that's minus 87.9. We can just add all those up. All right, so clear. So negative 393.5 plus negative 296.8, and then minus 87.9. I got negative 778. So they'll ask me a bunch of questions here. Okay. Answer the questions on the following page. Stuff like it's negative and it's going to be exothermic and it's going to have that downhill graph. Heat's going to be produced. That kind of thing. So basically, we're burning this. So that makes sense to me. Okay. Oh, that's it for this practice. Sweet. That only took like what, 8 hours? What are we on? How long have we been recording? I don't even know. It's not showing me. Oh well, I'll just hit stop. And we'll call it good. 55 minutes. I got 5 minutes to kill. Oh. Don't forget to do information literacy. When did we say this test was going live? I said this was going Wednesday to Wednesday. So I'm throwing it up tomorrow. Sweet. All right. So Wednesday to Wednesday, exam for November 28th to December 5th. Sounds good to me. I didn't even get to drink all my soda pop. IBC root beer. Love this stuff. That was great when I was a little kid. Mm-mm-mm. All right. We'll catch you next time and good luck and study hard. And I will see you on Thursday.